Okay, so for FRP number 2, we have a solid cylinder and it has a mass of m and a radius of r. It's going to roll down an inclined plane without slipping, and it will go up this other incline right here with the same angle. The cylinder initially starts at a height of h, and the incline has an angle of theta. Now part A wants us to determine the translational speed of the cylinder when it reaches the bottom of the incline. And for all these problems, we have to express our solutions in terms of m, r, h, theta, and g. Okay, so for part A, we want to find speed. So that's basically velocity. A relationship that I know that has velocity is kinetic energy, and I know that at the bottom, all the potential energy that the cylinder had initially will be converted to kinetic energy. So the essential statement to make is PE initial is going to be all converted to kinetic energy, and at the bottom, the kinetic energy is going to be, there's going to be two kinetic energy. There's KE translational, and this is at the bottom. And then there's also KE rotational, since the cylinder is rolling. Okay. PEI initial is m times g times h. KE translational at the bottom is 1/2 times the mass times v squared, which is what we're trying to find. KE rotational at the bottom is 1/2 times the moment of inertia of the cylinder times the the angular velocity. So represented by omega. So omega squared. Now the moment inertia of the cylinder I know is 1/2 mr squared, and I also know that omega is equal to velocity over r. So I'm going to substitute that into next, so I can solve for v. Okay, so I have mgh, those stays the same. Then I have 1/2 mv squared, this term still stays the same. And then I'm going to substitute I cylinder and omega in right now. So 1/2 times 1/2 mr squared, that's the moment of inertia, and omega squared. So if I sub this in that square, I get v squared over r squared. Okay, so at this point, there's a lot I can cancel out. I can cancel the m right now. The r's right here can also cancel, r squares. And so what I have is GH is equal to, okay, so these two terms now are exactly alike. This is 1/4 v squared, because that's all I have left here, and this is 1/2 v squared. So these terms can combine. 1/2 plus 1/4 is 3/4, and then the terms that follow is v squared. Now if I want to isolate for v, I'm going to times the reciprocal of this, which is 4/3, and square root everything. So my v, which is essentially the same as my speed, is going to be equal to the square root of 4/3 times g times h. So I did multiply by reciprocal and I square root everything. And this is my speed at the bottom of the incline. Okay, part B wants me to draw a free body diagram on cylinder as it rolls down the incline. Your arrow should begin at the point of application of each force. Okay, so part B. So here's the incline. So here, and here's the cylinder. All right. So for any object, there is gravity acting on it. So there's an FG, and FG is going to be applied right from the center of mass, so right in the middle, FG. On an incline, FG will have components. There is FG, FGY, and FGX right here. FGY will be cancelled out by Fn, so there will be an Fn to balance out FGY since the object is not accelerating in this direction. So Fn right here. And since the object is since the cylinder is rolling, that means there is a force of friction. So there is an F friction. Okay, so that is my free body diagram. Now part C wants me to derive an expression for the acceleration of the center of mass. Okay, so for this one, I'm going to use this kinematic equation. Vf squared minus Vi squared is going to be equal to 2 times acceleration times the distance traveled. Okay, so I know that the distance traveled from here to here is basically this length right here. This length is essentially the hypotenuse of a right triangle. So if I take sine of this angle right here, I get h over this. Now if I times this over here, I'll write it down. So if I take sine of theta, I get h over the distance. Now I want to have distance, so I'm going to times d over and then divide sine. So essentially my distance is going to be equal to h over sine of theta right there. So that's my d. Alright, now all I have to do is just plug in what I know. So my Vf squared, this is my V right, this is my Vf right here. And if I square it, I basically cancel out the square root. So I have 4/3 GH Vi squared. At the beginning, the object, the cylinder is not gonna move, so there is, this becomes 0, and 2 times the acceleration, which is what we're trying to find, and the distance is h over sine of theta. Okay, right now the h will cancel, and to solve for a, all I have to do is divide 2 and times sine over. So a is going to be equal to, if I times 2 over, or divide by 2, I'm going to get 4/6, which simplifies to 2/3. So 2/3. I still have h in my numerator, and then I divide, and then I times by sine of theta. So sine of theta, and that is my acceleration right here. Okay. Sorry, I don't know why my recording abruptly stops. Anyways, for part D, we are asked to find the percent of total initial energy that is transformed into translational kinetic energy at the bottom of the ramp. Okay, so to find the percent, we need to first find kinetic energy at the bottom of the ramp, translational, and we also have to find the total energy initial, and then we divide them and times by 100%. So first of all, I know that my KE translational at the bottom of the ramp is equal to 1/2 mv squared. Same thing as up here. Now for my total energy initial, I know that my total energy initial is just my potential energy in beginning, so PEI, and I know that PEI is m times g times h. Now these terms don't necessarily cancel out in variables, so I'm going to have to change this to something that matches this in the variables. I know that this mgh is going to be equal to 3/4 mv squared, same variables as this one, and here's why. So going back to part A, we had this relationship right here. GH is equal to 3/4 v squared. Now if we times both sides by mass m, we have this relationship. mgh, which is potential energy, is equal to 3/4 mv squared, and this is exactly what we're looking for, 3/4 mv squared. Now our terms will be able to cancel and we'll be able to get a percent. Okay, so percent is equal to KE translational at the bottom over total energy initial times 100%, and I'm going to sub in these for the ones right here. So this is going to be equal to 1/2 mv squared over 3/4 mv squared, then times 100%. The m's, the v squares cancel. 1/2 divided by 3/4 is the same as 1/2 times 4/3. 1/2 times 4/3 is 4/6, and 4/6 reduces down to 2/3, which is 0.6666666, and then you times it by 100%. That is 66.667%. Just rounding it up right there. Okay, now part E wants me to derive an expression for the minimum coefficient of friction between the cylinder and the inclined plane that is required for the cylinder to roll without slipping. Okay, so to do that, I'm going to use torque. I know that total torque, is equal to the total force that is perpendicular to the moment of arm times r, moment of arm, and this is referring to the cylinder, by the way. I also know that the total torque is equal to the moment of inertia of the cylinder times its angular acceleration, alpha. Okay. Now I know that the total force that is perpendicular to the moment of arm, right here, looking at right here, it's just F of friction. So I have F fric and times R. That's equal to, I know that the moment of inertia for the cylinder is 1/2 mr squared. I already defined it up somewhere up there, right here. And for alpha, I know that alpha is equal to A over R. So I'm going to plug it in right here, A over R. Now the reason I did that is because I know I can cancel all my R's right now. R right here will cancel one R right here, and the remaining R will cancel all with the R in the denominator. So what I have is F with friction is equal to 1/2 MA. 1/2 MA. Now I know that I know that I'm looking for the coefficient of friction, not friction, not the force of friction. So I have to define this in terms of the coefficient of friction. So F fric is equal to the coefficient of friction times mass of the cylinder times G times cosine of theta. That's basically what friction is in most inclined problems. Okay, so if I sub this in for f of friction, I have mu mg cosine of theta is equal to 1/2 times mass. I'm also going to sub in for acceleration, this right here. So 2/3 g sine theta. Okay, so at this point, I can cancel out my m's. My 2 right here will cancel with this 2 right here. And if I want to isolate for mu, wait, my g will still cancel right here. If I want to isolate for mu, I'm going to divide cosine over. So mu is equal to, so I still have 1/3 left. And then mu divide cosine of theta divided by cosine of theta is tan of theta. So mu is equal to 1/3 tan theta. And that is my answer for the coefficient of friction, the minimum. Okay, now part F wants me to, well, it tells me that the coefficient of friction is now made less than the value determined in part D, so that the cylinder both rotates and slips. Now I have to indicate whether the translational speed of the cylinder at the bottom is greater than, less than, or equal to the translational speed calculated in part A. Justify why. Okay, so I know that the translational speed will be greater than, and here's why. So the translational speed will be of the cylinder would be greater because a smaller coefficient of friction, a smaller mu, results in less torque being generated. Now remember that torque is equal to f of fric times r. So if mu is smaller, this will become smaller and torque will become smaller. So less torque is generated, and that's due to a smaller f of friction. Now this condition causes less energy to be transformed into KE rod, and with less energy into KE rod, that means more energy is going to be transferred to KE translational. So essentially, smaller mu k means smaller torque, less, and smaller torque means less KE rod. Less KE rod means more KE translational there. Okay, now part 2 of part F asks me to indicate whether the total kinetic energy of the cylinder at the bottom of the incline is greater than, less than, or equal to the total energy for the previous case rolling without slipping. Explain and justify your answer. Okay, so I know that my total KE at the bottom will be less than the original scenario if it was rolling without slipping. Would be less than because since the cylinder slides, some energy will be lost from the system as heat. So basically there will be less energy in the system, and that energy will become heat instead as it is sliding. Okay, so part G now asks us, or it tells us, the cylinder then continues to roll up the other side of the ramp, draw a free body diagram, assume the surface is the same throughout the entire problem. So again, there will be friction if the surface is the same. So here we go. Part G. So here's the other side of the incline. Here's the cylinder. Once again, there is FG acting on it as there is for any object. There's components to FG. There's FGX pointing this way now, and there's FGY. This is FGX. The object does not accelerate in this direction at all, so there will be a force counteracting FGY, and that is Fn. As I said before, there is friction, and friction always points in the opposite direction of where the object is moving. Now if the object's moving this way, it's moving up the ramp, that means friction is going to point down the ramp. So right here, that's F of friction, and that's our free body diagram.